Okay, so I'm going to walk you all through how to set up a model for the flow over a sphere. This is using the latest star CCM version. So what you want to do, what I like to do is I'll use two parts. I'll create a sphere. Here it gives us an origin. This gives us a radius. This is a coordinate system, and this is how refined we want the surface to be represented. Medium should be fine for this. So we created a sphere. Up here, we come to this and look at geometry, and then we can actually look at the sphere that we have. So again, this is a sphere with the origin of 0, 0, 0 and has a radius of 1 meter. We could shrink that to 0.1 meter and make it a little bit smaller. Then what we need to do, so this is a sphere that we're going to be resolving the flow around. So then we need an outer domain. A convenient outer domain is a block. So it defaults to snap to the size of that sphere. But what I'm going to do is push it as far away as I can. So I'll push it out 10 meters in the X direction, Y direction, Z direction. And again, this is going to be in all directions. So we have this box on the outer domain of it. Hit close. So we have a sphere, a little sphere, and a huge box. One thing we want to do with this box is break up the surface. Very easy ways to do by angles. And the reason why we do this is because we want to understand orientation. So if we want X to be positive, maybe Z is down, we could kind of see how we have different surfaces. So I might pick off this one and actually rename it to be an inlet. These, maybe I could actually combine these and call them sides. And I could call this one an outlet. We need this to be able to assign boundary conditions. So we could go to these things called operations and do a Boolean operation and do a subtract. And the idea here is to take a cookie cutter approach. So you feed it two parts and you say, what's the target? So you feed it. So what it does is when you feed it those two parts, it says, I'm going to work with these two parts. And the target is going to be, what is the base thing? So in the context of a cookie dough or a cookie cutter, block is the dough you've rolled out on the table, and sphere is what you're cutting out. So I do it on the CAD and I execute it right when I hit OK. So now if we go to our scene, I come up here, change surface from sphere and block, and just look at the subtract. I could click on this thing and I could see that we have a sphere cut out of the box. If I go on this subtract, you can see it has an inherited parts. I have an inlet, an outlet, sides, and a sphere. So this ultimately becomes where we operate on. So I'm going to right click on that and say assign parts to region. And I'm going to create a region for each part. And I'm going to create a boundary for each part surface. Again, I need that so I could specify boundary conditions. And I think it'll become a little more clear in a minute. So now I have this thing called a region. This is a computational domain, and it has boundaries that we could start assigning boundary conditions to. Prior to doing anything more, I'm going to make a physics domain, and I'm going to select models. I'm going to say we're doing a three-dimensional model. Let's just do gas flow. We'll do a segregated flow solver. It's a numerical approach. The constant density, and we'll do steady to make things fast. And we'll just do laminar. Okay, I'm going to hit close. Now we have a basis for the physics continua. Okay, so now let's start moving on to the meshing part. We have a computational domain. What we need to do is make a computational mesh. One of the new features here is you create what's called an automated mesh. This is a 3D version. So we create an automated mesh in 3D. We create it on the domain, the computational domain. So again, this is a block. This is a sphere. They're unrelated. We needed to really put it on this one that's been connected. So we need to do a few things. We need to do a surface remesher. We can do some of this stuff, not really needed for what we're doing at this point. And then what we could do is choose either a trimmer or a polyhedral mesher. We'll just choose this. We'll choose a prism layer mesher. This is needed for, or we'll actually do an advancing layer mesher. This is kind of needed for creating a nice boundary layer mesh. So we have this automated mesher. What we need to do is set some guidelines here. We can do a base mesh size of 1. What I'm going to do is make a max size of 100 that is connected to the base. I'm going to make a surface, minimum surface size. It's by default set to 0.1. It's way too small. We have a, let's see if we could get a mesh to show you. So I click this little thing, it creates a mesh. What I need to do is get another view that actually starts looking at the mesh. What you see is these polyhedrals or arbitrary polyhedrals. So I can't really see anything that's going on. We could either look through it, or we can create a surface that we could start looking at stuff on. So we go to derive parts, new section, plane section, and I'm going to make a plane section through, let's say, y = 0. Have it normal to the y direction, 0 here. And I'm going to create a new mesh displayer. What I'll do is we'll be able to see it. So to get rid of this stuff, I just right click on it and hit hide. And you can see I made a mesh. I'm looking at the mesh through the center plane. We can still see the inlet and outlet. And if we zoom way in, we could see what is a sphere. This is absolutely not a sphere. And the main reason is because this target surface size and minimum surface size is set. The minimum surface size is 1.1 meters. We change it to 1 or 0.01 meters. Remember, what we'll see is we'll start seeing this sphere evolving. So you just have to remesh and tweak these parameters until we get something that we're pretty happy with. So now it looks like a sphere, but then we have this really bad, what's called a prism layer. We also have a prism layer out here, or we really don't have. So these prism layers are aimed to capture a lot of sharp gradients in the velocity and boundary layers. So we don't care about them out here at the far field. So what we do is go to the regions and look at these boundary conditions. What it does is defaults the boundary conditions that are walls to get these prism layers. So I turn the inlet to an inlet, outlet to an outlet. The sides, I'm just going to call them a symmetry plane. We have boundaries that are very far away, so that works pretty well. And leave this as the only wall. We still have a problem with these prism layers being way too big. So we could go into the automated mesh settings, go to number of prism layers. Typically you want at least 21. You want a stretching ratio, not quite 1.5, 1.1 is probably pretty good. And then this relative thickness. I'm going to make it absolute. And I'm going to say, okay, instead of 1/3 of a meter, if this is 0.1 meters, that distance, we probably want it on the order of 0.02. So we remesh, and we'll take a look at it. What we'll see is a lot of these things won't change on the surface, but these prism layers started to form. So now this is a decent starting point for a mesh. I'm going to just show one more trick. One thing that happens is flow will be nice and attached, and inviscid, and then in the wake, it'll be highly viscous, and that typically demands a little bit more mesh. So what we can do is add a little refinement. I'm going to add what's called, I'm going to add a cone. I'm going to put it right behind this thing. So 0, 0, 0 is the center of the sphere. I'm going to give it a starting radius of 0.11, a little bit bigger. And I'm going to make sure that this goes to the right. I'm going to go back about 10 radii downstream. No. And I'm going to make it about 0.125. So you can see we have this region downstream. And what this region could be, what could be done with this region is we could come back to the meshes, go to make a custom control and a volumetric control. Select that specific part. For some reason, I'd never made it. Looks like it's kind of, oh wait, I had to create. Okay, then I come here, select this part, select the cone. Then I could just make a mesh that's a little bit, so I go here and I focus on making customized settings for the polyhedral mesher. And I can make it, so 10%, that's this length scale. We need something on the order of 1%. So I remesh, and what we'll see is a mesh density of about this size all the way through that cylinder. It makes a little bit larger mesh, but it'll better capture some of the unsteady flow features. So right now we're about 100,000 cells. Maybe just the base mesh, and we'll see what happens when we get the boundary layer. So I'm going to just make a suggestion. If you have, you have to be very careful on how you set these parameters. Right now, you could easily end up with like by changing, these things, number of cells scales by like a factor of 10 for every time you double it, which means you can easily change a parameter and get to a really big mesh. It'll just break your computer. Here we only have 137,000 cells. We have a very good starting point, and then it's something to look at. Okay, now we have a computational domain that involves the mesh. Now let's start getting a solution. So we have a boundary inlet. If you look through here, they have a couple options. Velocity specification, it says, so what it tells us is on this inlet, we want to specify velocity, specifically magnitude and direction. So magnitude we can make, for example, 10 meters per second. Direction, it defaults to boundary normal. Okay, block outlet, we're just going to leave that at the pressure. This is a gauge pressure relative to some other thing. It really doesn't matter or drive the solution. It's just forcing that pressure on that boundary. Sides have pretty much nothing. This doesn't really have much either. We're actually at a good state to start, with the exception of maybe an initial condition. Because we started out at 10 meters per second, we might start this off with an initial condition of 10 meters per second. Hit this green button, which initializes. So I go to a scalar scene. This is where we start looking at the flow field. You could grab some of these features like a gear-derived part, drag it over here, create a new scalar. Right-click on it, and let's look at velocity, specifically velocity magnitude. Hit OK. This shows us our velocity magnitude. It's 10. So if I hit clear solution, it'll go to nothing. And remember, our initial condition was 10. So the other thing we could do is create a surface. So I select this, drag it in here. I'm going to put it on scalar 1 since nothing's there. This is a scalar 1, and I'm going to look at pressure on there. So now it's 0, just because that's what our initial condition was. Next thing we do is we hit this little running person, and it starts evolving the solution. And you can see we have a nice solution of the flow over the sphere. We could come to this and start messing with some things. I like to switch automatic to smooth filled here and here, and then everything looks a little smoother and nicer. All right, so one more thing I wanted to show you all. So here we have a little bit of a flow separation, which we're expecting, and this is going to lead to some of those complexities and the demand for that wake resolution. So if I look at the mesh, you can see we have a finer mesh capturing all the gradients up here. It's pretty sharp gradients, and they really need to be captured reasonably. Okay, last thing, how do you get things like forces out of this? Here we go to something called a report. So I go to report, right click. I actually have to stop the model. I go to report, right click, new. Go to flow force. I could create a force in the X direction. So that's our X direction. It's going to be drag. I could select the part. And what it does is does a full-on integral of pressure and viscous forces, and it gives us a value for drag. So it gives us a pressure, viscous, and net. We can copy this, change the name, call it lift. Lift could be either in the Y or Z direction in this scenario. I think we said Z was down, so we'll call it lift in the negative Z direction. So we can change this to 0, 0, -1, which would be our lift. I can select both of those, right click, and hit create, monitor, and report, and a single plot. So I'm going to clear the solution, reinitialize, and that gives us our initial conditions. I'm going to hit go. You can see the solution evolving. If we look at the report, we have our drag and our lift. Okay, one of my pet peeves is when when people make plots and they make a plot that looks like this, and really all the excitement, this is called the transient part of the solution, nothing exciting is going on. You zoom into here, this is where you should be focusing on. Nobody cares about that. Don't almost never plot that. There's zero value to looking at it, and it hides what's really important. And that's in this history of the forces that you see here. So if we look at drag, you can see it's oscillatory. It's a steady, so if we can see a similar behavior with the lift. That oscillatory nature is expected for these bluff body flows or flows with flow separation. And you know, in reality, when you see this and you look at your residuals and they aren't converging, what it tells you is that you need to go from a steady to an unsteady model. So for the time being, we're just going to stick with steady. Unsteady will take us a little bit more time, but just keep that in mind. So this is basically a good starting point for how to start simulating the flow over a sphere. You could use this kind of approach for almost anything. Really all you need is a domain and a CAD that you want to model, and make sure you kind of utilize some of these models correctly. That's kind of the difficulty part. All right, that's pretty much it. I'm going to sign off. I think this will help get you started.